questions you might have.
No worries. Thank you very much. I still have some time for questions.
Good.
There's you, John.
Hi, Jonas. Can you hear me?
Yes, I can hear you.
Okay, thank you for interesting talk. I want to ask you, how did you get the solid line in the Pareto optimal trade-off? Pareto optimal front. How did you get the solid line? Yes.
Basically, this is determined by a genetic algorithm which does multifunction optimization. So this is a purely numerical result, the solid line. For these ones, these are actually analytically computable by assuming that one of the boundary reservoir densities is fixed to 1, and then we can vary the other one. And if we vary the other one, we actually slide along these optimal lines. And the different lines are just simply combinations of fixing either the left boundary to 1 or the right boundary to 1 and then changing the other one. But this one is purely numerical through genetic algorithm.
Okay, thank you.
Yeah.
Okay, then Tom.
Thanks for the talk. Why did you make it an exclusion process? I mean, presumably that's not really relevant for the hunchback or whatever in the Drosophila.
Yeah, good question. Basically, for simplicity in this case, there is a preceding article by one of my colleagues, Prashant Singh, and he basically did the computation of how you would compute the positional information for many different processes. So also just non-interacting diffusive particles, zero-range processes, etc., inclusion processes even. So for this one, it was just basically a proof of concept model which provided us with the easiest computations. Yeah, but it's easily extendable to all the aforementioned models that I said.
Okay, and then we have David.
Yeah, nice talk. I guess thinking about the monotonic functions, one of the appeals of them, I think, is that you've got this invertibility, so you can kind of, at least in principle, go from a readout to an answer of where you are. Can you talk at all about why non-monotonic would not be bad?
Yeah, basically that's because of the local gradient of the density profile. So what you could do basically is if you go back to this equation, you can actually change the integration variable back to G and then write everything. I removed the slide. You can write everything as an integration basically over 1 over the derivative of the density function itself. So basically that means that if you have very sharp local gradients, you would be able to very quickly deduce where you are in the system, even if you have the non-invertibility. So at some point, this non-invertibility becomes less important with respect to the local gradients being just extremely high. So for the non-monotonic profiles, if you would look, for instance, for this one, if we would increase the reaction rates in the system, for instance, even more, then all of the positional information would basically be concentrated in two peaks at the sides of the system, which would convey the largest amount of positional information in that case.
Cool, thanks.
Yeah.
Okay, thank you very much again, Jonas.
Yeah, thanks.
And we now have a 10-minute break. So we reconvene at 45, whatever hour that is in your time zone. See you then.
Hey Patrick, I think
Udo has appeared.
I think Udo's on the call, so I don't know if that means he's available to chair. Have you confirmed?
Yes, I can confirm. Can you hear me, Tom?
Yes, I can. Brilliant. Thank you.
Okay, good. I will chair second round.
Wait, back from your emergency meeting.
Yes, back.
Very good.
Just in time. Und das Video geht, glaube ich, nicht.
We can't see you yet.
Yes, I
I
see that.
Just a black screen. It's maybe your webcam is covered or anything.
Okay, now it works.
That looks better, yes.
Yes, was covered actually. Needed help to uncover it. Okay,
I'll be right back.
okay, good.
Ja, können Sie mal noch die großen Jalousien runterlassen? Die ganz große von draußen.
Das kann ich gleich machen. Ja, weil das ist ein bisschen zu hell. Yeah, so welcome back. I'm Udo Seifert from Stuttgart, and I'll take over as chair for this second part of the Biophysics Active Matter session. Can you briefly confirm that you can hear me?
Can hear you, yeah.
Perfect, thanks. And we'll start with 3 lightning talks, and the first one will be given by Ramón Nartallo. And I guess you have, yeah, you can start sharing your screen. Perfect. Okay. Yeah, so
Okay,
let's
you ready to go?
start. Go ahead.
Okay, so hi everyone, I'm Ramon. I'm a PhD student at the University of Oxford, and I'm going to talk about something maybe a little bit different here, a structural perspective on non-equilibrium brain network dynamics. So there is recent work that shows that neural dynamics at large scale, so recordings from humans, macroscopic recordings like fMRI or MEG, can be modeled as a process in a non-equilibrium steady state. This can be formulated either as a discrete state Markov process, so using clustering or hidden Markov models to assume that this continuous data comes from an underlying Markov process, or using a stochastic differential equation framework. So these are stochastic continuous dynamics. And what's really interesting about this is that the entropy production rate, or the time irreversibility of these processes, shows interesting variation across conditions. So here, when entropy production doesn't necessarily mean something physical, it's not a question of energy being dissipated, but it's something about the dynamics that seems to vary between tasks. So we see higher entropy production and irreversibility in tasks compared to rest. It varies across conscious state. So we see more irreversibility in healthy controls compared to patients in comas or unresponsive wakefulness states. Entropy production decreases across sleep stages, and it decreases in Alzheimer's disease. And these are using a lot of different measures, some direct measures of irreversibility, some more indirect, looking at cross correlations, etc. And so there's a lot of work looking at these kind of differences in the level of irreversibility in brain signals as of 2021 going forward. But we were very interested in how this relates to brain network structure. So brain network dynamics are traditionally modeled as network dynamical systems on a symmetric undirected network. So this is because of the way that we extract these networks from data or from imaging in the brain. But non-equilibrium dynamics emerge from broken symmetry and irreciprocal interactions. This is kind of well known in condensed matter theory. And so what I was curious about was, what is the role of network structure on the properties of this non-equilibrium steady state and on the entropy production rate? So going off the hypothesis that many processes on symmetric networks satisfy detail balance and on directed networks violate detail balance, does more directedness in a network imply more entropy production and more irreversibility? And then can we use this concept of more asymmetry to explain these irreversibility variations in the brain in a way that is more relatable to traditional neuroscience? So something about a reconfiguration of networks, as opposed to this more esoteric quantity entropy production in this case. Oops. Yeah. So first we started with some kind of simulated results. So we looked at the Ornstein-Uhlenbeck process, the Ising model, and the random walk. And we can first consider basically a toy model with just 2 nodes. And you can look at the entropy production here in the Ising model or in the Ornstein-Uhlenbeck as a function of the 2 weights. So you can see this diagonal line through the middle is when those weights are equal. And so that's where you have detail balance. And as you get more and more asymmetric, you get more and more entropy production. This is linear for the Ornstein-Uhlenbeck. This is nonlinear for the Ising model. Then for larger networks, we basically came up with this scheme to interpolate between an asymmetric network and a symmetric counterpart. So at epsilon equals 0, we have a symmetric network. As you increase epsilon, you get more and more asymmetry. And as we can see, you get more and more entropy production. So the y-axis here is entropy production. So at least in these kind of simulations for these 3 processes, we show that more directedness leads to more entropy production. But we wanted to analyze this also in human neuroimaging data. And it's difficult to both extract a network in a high-dimensional system and measure the entropy production. These are both 2 hard problems. So we took an approach that basically is modeling it with an Ornstein-Uhlenbeck process. And you can either have a kind of a general Ornstein-Uhlenbeck, or you constrain it to a network. So in this second model, A would be a positively weighted network of connections. And then if you discretize this process, it just becomes a first-order autoregressive process, which can be fit very easily with least squares or with convex optimization to recover the drift and the diffusion of this Ornstein-Uhlenbeck process. And given as there's an analytical solution for the entropy production, we can then measure the entropy production and study the structure of this network A. And what we find is this result from the literature. Here, phi is the entropy production, which is that you have increased entropy produced in task compared to rest. But we can also show that this occurs, at least using this linear model, because of increased asymmetry. So these other four figures are measures of asymmetry, different measures. So you have some local asymmetry measures, some global asymmetry measures, some spectral asymmetry measures. And we can see that across the board, we have an increase in asymmetry of this network that is driving the increase in entropy production. And so this allows us to take this result that hinges on a quantity that's not well understood in network neuroscience, entropy production, and put it in terms of things like asymmetry of brain network connections. Once we have this inferred network, we can study its structure. So we can do things like trophic analysis for networks. So this is like ranking networks in a directed network, ranking nodes, sorry, in a directed network in terms of their overall level in a top-down flow. And we find basically which sub-networks in the brain are moving up and down the hierarchy. So yeah, you can see, for example, the dorsal attention network in the brain is moving up the hierarchy. And that can only be analyzed if you have this asymmetric connectivity, which we are inferring with this autoregressive process. So another approach that uses irreversibility in network neuroscience is something that we published recently, trying to infer higher order interactions. So in network science, we're traditionally interested in pairwise interactions between units, but increasingly in complex systems, people are interested in these higher order interactions. So this is where you have sets of 3 or 4 nodes rather than just 2. And it's particularly hard to identify these interactions in data because traditional measures like correlations are limited to be pairwise. And so I had the idea to use irreversibility to try and infer significant higher order interactions. So the idea here is to begin with a trajectory. Let's just say this example trajectory is in 3 space, and you can project into all the possible sub-interactions. So you can look at the dynamics just of X, just of Y, just of Z, but also all the pairs and then the triplet itself. And the idea here is that a more irreversible interaction between a set of variables corresponds to a more significant interaction in the brain. So in order to measure this irreversibility in MEG data, we came up with the DIMVIGI framework, which is an extension of Lucas Lacasa's work using visibility graphs to measure irreversibility. So what you basically do is you construct a directed visibility graph from a time series. And the idea is that for a reversible time series, the in and the out degree distribution of this network should converge. And so their divergence is a direct measure of irreversibility. We extended this to the multivariate case by building a multi-layer graph where each layer corresponds to a variable. And then you have a joint degree distribution across your layers. And so if you're interested in the interaction between a particular set of k variables, you just have to calculate the in and the out degree distribution joint over those k layers and measure the divergence. And that's a measure of irreversibility of those particular k variables. And so we applied this to MEG data that was recorded from participants listening to music in an MEG scanner. And we had their brain activity parcellated into 6 key regions of interest that you can see in this graphic A. Then we were able to measure the irreversibility of every single interaction within the system. So the irreversibility of each individual interaction, all of the pairs, the triplets, quadruplets, and quintuplets. And we find results that made sense and that were very interesting. So first, we find that higher order processing regions, like the hippocampus on the left and the right, are more irreversible than sensory regions. Here, darker colors means more irreversibility. We found that pairs on the same side of the brain, so this right-hand pair and this left-hand pair between the auditory cortex and the hippocampus were more irreversible than, say, the 2 auditory regions together, which suggests that they're involved in some more significant interaction. And we have hemispheric symmetry across all the orders. So if you look at the pairs, the triplets, quadruplets, we have hemispheric symmetry between the left and the right side of the brain, which was a result that we were hoping for. If this didn't happen, then these results would be a bit weaker. But again, you can see a third order. If you look at the triplets, you can identify which particular sets of 3 are significantly interacting. So you have the ventromedial prefrontal cortex and then the corresponding pair on the left or on the right. And then at fourth order, you have the significantly irreversible ones, are the two medial regions with the corresponding pair, either on the left or the right. And then at fifth order, it's a bit harder to interpret the results, but we can see that if we remove the ventromedial prefrontal cortex, we have a less irreversible interaction, which goes well with our knowledge of the neuroscience, which says that the ventromedial prefrontal cortex is very important in these task-based activities. Okay, so that's quite quick, but some conclusions. The brain can be modeled as a stochastic system in a non-equilibrium steady state. The level of entropy reproduction irreversibility varies in these interesting ways between conditions and seems to be a good correlate of cognition or consciousness. But we need to kind of interpret that in more concrete ways because we're at a macroscopic scale here and we're not talking about entropy. So we tried to show that the entropy production can be explained in terms of network asymmetry and therefore requires consideration of connection directedness, which is something that is not really done in network neuroscience and should be. And we showed that irreversibility can be used to infer which interactions are significant across different orders. So thank you very much for listening. And if you're interested, here are the references. And we recently wrote a review on this topic about non-equilibrium physics and brain dynamics, which is out as a preprint if it's something that you find interesting. So thank you very much.